A background in quantum physics, condensed matter theory, and more recently machine learning. And yeah, so first of all, thanks Amir for the invitation. So this is a great pleasure. Such a intimidating audience, right? A big bunch of nerds.
You're used to it.
Thank you.
But still, like, I never had anyone introduce themselves, right? Like just right before. So it sounds like, wow.
That's one of our intimidation techniques.
It worked. Yeah. So yeah, so I'm here to tell you about learning quantum states with generative models. So this is basically a talk about how to. Okay, so we'll have several ingredients, but one of them is how to translate a generative model into a quantum state, pretty generically, and then the second thing is how you can use this for reconstructing the state of a quantum device. Okay, so quantum devices. Okay, we're building them. There's a big bunch of companies trying. They promise a lot of things, and that's good. But we can test, right? Like whether what these machines are doing correspond to what they say they should do. Okay, and so this is a discussion that we can have if we have the right tools and so on. And generically, this type of reconstruction techniques work well when the systems are really small, because basically a state is, if you want, represented in terms of an exponentially complicated wave function or density matrix. And so as these systems grow, as these quantum computers grow, or these quantum devices grow, the problem of reconstructing the state becomes really tough. It's really an exponentially hard problem. But if you use machine learning and this generative models and so on, you can alleviate, or you can try to make progress and then try to study systems that are bigger than what you can approach with traditional reconstruction techniques. Okay, like exact quantum state tomography and so on. So this is what I'm going to tell you about, basically. So this is not working.
It should work now.
Yes. So I'm from this from the Vector Institute. I had a couple of slides about what it is, just in case some of you don't know. So Vector is an independent, non-for-profit entity, and it's dedicated to research in AI, artificial intelligence. And it launched in 2017 with support from the government of Ontario, Canada, and the private sector. So it's kind of like a collaboration between private and public. And the idea is to generate excellence in machine learning for the region. So that's great. So this is the faculty. So most prominently Jeff Hinton, Rich Zemel, Alan, and a big bunch of other people. This is how it looks. So it's a big bunch of computers and desks.
Are always balloons?
Typically, no, not really. It's just, there was some open house, so we had balloons. Right? So I'm also hiring, so, so if you, as many of you. So we have two PhD, or I have two PhD positions on short-term visits. So if you're interested in things at the intersection between quantum physics, condensed matter theory, and machine learning, just let me know, okay? So these are my real machine learning friends. So Leandro, Roger Melko, Giacomo, Essen, all of them. Giuseppe, Matthias Troyer, Peter Brocker, Simon Trefsten, Guillermo Mazzola. Right? So, so I'm going to introduce why I think machine learning can help us do this. Okay, like help solve problems in quantum physics, which is one of the things that I try to do. Okay, so the idea is that when you're trying to specify the state of a quantum system, you typically require resources that scale exponentially in the number of degrees of freedom of the system. So for instance, if you have n spins or n electrons, then if you want to specify the state of the system, you need a vector with 2 to the n components. Okay, So that's a lot, right? Like if n is, for instance, 45 particles, then we can still use today's best supercomputers to try to solve these problems or to manipulate these wave functions and so on. But that's using the best of the supercomputers that we can have. So here I have Recon is one of the biggest clusters. At least it was the biggest in 2011. And you can only handle 45 particles with that. And this, I don't think this audience needs a reminder of what exponential growth means, but let me just tell you a number, like a random number. It's not really random, but so storing the state of 273 spin system, so 2 to the 273 requires a computer with more bits than there are atoms in the universe, right? Like, so what does that even mean? But very important technologically relevant problems in chemistry, in condensed matter, quantum computing are just way larger than 273, right? So what do we do about that? So one idea is use quantum computers, but as Peter mentioned, they don't work, or as he suggested. So let's say that we're, or not me, but people are trying to figure out how to build them properly and so on, or but we still don't know how to scale them. Okay. However, nature is compassionate, even though I don't think nature cares about what we think, right? Like, but let's say that it's compassionate in that so many body systems can be typically characterized with a number or with an amount of information that is smaller than this maximum capacity. So it's a lot of, I mean, if you want, the states are very compact. So you don't need typically 2 to the n if you want to study bigger systems, and so long as they have some particular structure. Okay, so now you start hearing like these ideas and think about machine learning, where it works also as long as you have structure. Okay, so this is, if you want, the first reason. Okay, and that structure or that compassion is the reason why we can study some systems using Monte Carlo simulations, right? Like, so quantum Monte Carlo simulations and tensor networks exploit that fact. Okay, so in quantum Monte Carlo, what we do is we explore this 2 to the n, this exponentially complex state space, and we do it stochastically, right? Like for some quantum systems where this applies, and then so we can make progress, compute correlation functions, make predictions for significantly large systems. So that's good, but the problem is it doesn't work all the time. Okay, so what about the systems for which the QMC doesn't work? Okay, and then tensor networks, they're very successful and very useful. So for instance, NPS, matrix product states, what they do is they exploit this states with some structure. They have low entanglement. Okay, and then so you can, for instance, take a giant tensor like this one and factorize it in terms of this smaller tensor, so these balls here, and you go from an exponentially complex thing to a polynomial number of parameters describing the same system. Okay, and this works and is very efficient and useful, but it doesn't work for all systems, right? Like, so again, what do we do about the rest? So now, this is the point, like the most important point of machine learning, right? Like, or like how this relates to what we're trying to do. And the idea is that the machine learning community deals with equally high dimensional problems, right? Like, so for instance, if you take MNIST, which is a data set of handwritten digits, it's like, I think, 28 by 28 images. And if you take binary MNIST, the state space where these images live is 28 by 28 to the 2, if you binarize this data set, and that's huge, right? Like that's way bigger than 2 to the 273, right? And they still battle this curse of dimensionality in machine learning, and they have like surprisingly impressive results, as you all know. Okay, so that's the idea, right? That so in here I have quantum Monte Carlo, which can deal with some problems, tensor networks, it can deal with other problems, and what we're suggesting is, can we use neural nets to tackle these problems, right? And it turns out.
Can I ask you a stupid question?
Yes.
So if I want to summarize this slide, are you saying that it's true that for quantum systems, the dimensionality of the space is increasing exponentially versus the number of degrees of freedom?
That's right.
But it's not information dense, if you like, and you can use smart techniques like what we do in neural nets often to go to spaces where, you know, there are dense representations of.
I think that's a perfect summary of what I said. Yeah.
Does that mean that by taking that kind of approach, you are losing some exactness or accuracy? Like there's some approximation
Yeah.
that's happening.
Yeah, exactly. You cannot hope that this will be exact, but you can create really great approximations to states that have some structure, right? So you give up on having a perfect representation. You focus on a tiny corner of this huge state space, and so you give up on some things. That's right.
So your approach with neural network works for low entangled systems, not?
No. So neural nets are not necessarily restricted by entanglement, for instance, as opposed to MPS.
Because if we are removing some part of information, then we don't have, if it's like highly tangled, so how much?
So it turns out that some generative models, if you understand them as a neural net, they have a lot of entanglement.
Oh.
Okay, but the restriction comes from something different that we still don't know. Like if you want, what quantifies the power of expressibility of this system or these neural nets? From the point of view of a quantum system, we still don't know. That's research right now.
I kind of remember what entanglement is from theoretical physics, but it was 15 years ago, so I'm hoping you can remind me.
Yeah, so entanglement is quantified by okay, so let me first tell you what a state without entanglement looks like. So a state without entanglement looks like as a state that you can factorize in terms of the states that are independent for each of the individual degrees of freedom n, and then a state that has entanglement, you cannot factorize it this way. And there are many different ways of quantifying entanglement. But basically, it's just a quantity or a quantity that tells you about how much you can know about a fraction of the system if you trace out the rest. Okay, that's kind of like the idea.
Can I try to? So essentially, it is when you have more information about your whole system than some of the information about individual components of it. So it is kind of like correlation, but much stronger in quantum.
That's right.
Thank you.
Sorry. So you are talking about quantum states, then it's like an ensemble. It's basically in the language, it's dealing with density matrix instead of just one specific quantum state.
Yeah.
Okay.
Yeah, so I didn't speak about mixed states, so I've been talking about just pure states. So I mentioned you have a vector with 2 to the n components. The more general states that you find in nature are described by an ensemble of states that's called a pure mixed state. Okay, and these are described by matrices, 2 to the n by 2 to the n matrices with they're Hermitian matrices and they're positive semi-definite. So what I'm going to talk about is not restricted to pure states. We can deal with pure as well as mixed states. Okay. Let me go ahead because otherwise I won't finish. So yeah, so we have that. Like, I just want to mention that there's a lot of work happening right now at the intersection between physics and machine learning, and so this is a list of papers. So I won't discuss them. So before that, let me just introduce a slide about notation that we use. So I like using these balls. So a scalar I'm going to represent as a ball, okay? And a ball with an index, which I represent with a stick. So this is VI, this index I is represented by a stick, that's a vector, okay? And a matrix is a ball with two indices, ij, right? Like wij, that's a matrix. And then, so if I have two of those together, then it means multiplication. And if I join a line, it means sum over those two indices, okay? So for instance, this thing looks like that, which is matrix multiplication, all right? And that is, again, a new vector, right? Like it's just a ball with just one index, okay? So, so that's matrix multiplication. And if you have, for instance, the norm of a vector is, it looks something like this, right? Like a ball and the second ball, so C, and then you sum, and then that's the, again, if you surround this with a bigger ball, you see no sticks, right? Like, so it's like a scalar. So that's the norm, okay? And then, for instance, trace of matrix multiplication, so then you have this, and then this is matrix multiplication as in here, or similar, and then trace is this part, okay? So I use this notation a lot because, for instance, matrix product states, that's how you understand them and so on. So I like this type of, like, it's very fast for linear algebra when you have lots of high-dimensional objects, okay? And so on. So this is a notation, but now let me tell you about how to do these reconstructions and what quantum state tomography is and so on. Let me go fast. So quantum state tomography is the process of reconstructing a quantum state through measurements, right? Like, so you take a quantum system and then you take measurements on it. Okay, you heard about this before, maybe in the news, that if you take a state or a quantum system and then you measure it, you destroy the state, right? This is almost every week on the news, right? Like the quantum computing stuff. So what we do instead is, okay, we have the state, we prepare it several times, many times, and we measure it, we destroy it, we measure, we destroy, and so on, and we collect this statistics. And then the idea is, if we take those measurements, can we reconstruct the state? Can we tell what the state that we're preparing looks like, okay? And this is useful because we can characterize, for instance, optical signals, diagnose errors in the preparation of the state, we can also verify that there is entanglement in the state and so on, which is crucial. Anyway, so this is, if you want, the gold standard for verification of these quantum devices, right? Like people say, we built a quantum computer, let's just benchmark and verify that they work. Okay, so that's the idea. And the idea is that there's a lot of progress in controlling these quantum systems, right? Like this happened, I think, beginning in 2010, roughly. There's a lot of progress, new measurements, almost arbitrary measurements, and they're performed with, I would say, great, but with some quotes, with great accuracy, right? Like, so we're scaling beyond a point where, like, this reconstruction schemes that are traditional cannot work, because the bottleneck now becomes the estimation of the states and this curse of dimensionality, this exponential growth in the size of the state space. And here I have a few examples. So this is trapped ions. This is Google Bristlecon, so the 72 qubit quantum computer they have. This is D-Wave. They have 2,000 qubits. This is called Atom. So they're scaling this systems pretty fast. So can we certify what they're trying to construct beyond 20 qubits, right? So that's the idea.
Is the Google one circuit-based?
It's gate-based, yes. So you need some ingredients. So you need a quantum system that can be prepared repeatedly, right? Like, because once you measure, you destroy, but you want to measure a big bunch of times. A set of measurements, training procedure, meaning taking this data and producing a state or an estimate of the state, and then so you can use the full density matrix that scales exponentially with the size of the system. You can use matrix product states that scales well with the size of the system, but it has some limitations. You can use neural networks, so that's what I'm going to tell you about. Yeah.
That's a question. If the size of like state matrices that you're applying this to is like bigger than the number of atoms in the universe, how do you, so is this for something, for like validating something that you have a theoretical understanding of, so you can simulate, or like you can calculate already, not simulate per se,
Yeah.
and you're just like doing the reconstruction to see that the device does as it claims to do?
That's
or?
right.
Okay.
That's right. And that's an important point because if we could validate every quantum computation, then why building quantum computers, right? So we will be able to validate some states, and then we trust. Okay, so we need to be able to validate against something that we can produce with our poor man's classical computer. Yeah. Right. So, and then we do a certification of the state. That's a typical protocol. So traditionally, as I said, it requires exponential resources. So if you, for instance, do a linear inversion, then you're inquiring in an exponentially bad, exponentially poor inversion problem. So I'm not going to go into these details right now. So just to tell you that traditionally you can go up to 20 qubits or 20 spins with these techniques. And there's also another one which is also traditional, where you use maximum likelihood estimation, the same one that we use in machine learning, that also requires an explicit density matrix. So you're already by definition, so you write down the most general 2 to the n by 2 to the n Hermitian positive semi-definite matrix, and then you maximize the probability of the observations that you made. And then you produce an estimate of that matrix. So that's also exponential in the parameterization. So that's bad. Or if you want, it's great because you can represent any state, but it's very expensive. So you cannot go past a few qubits. All right. So how to make this quantum state tomography efficient? So that's what I'm trying to do, and what people have tried. So some people use matrix product states, and they're successful in one dimension. Okay, so they've shown that this is pretty great if the spins lie on a one-dimensional system or path. Okay, or if you want the interaction between the system lie on a one-dimensional graph, so they are successful, and they started the field basically. And then we introduced parameterization that is based upon restricted Boltzmann machines, which are not very popular in classical machine learning right now, but we find them pretty useful because they're easy to handle and easy to analyze theoretically. So we can even put bounds and, for instance, how much entanglement they can carry and so on. So we published this paper, this neural network quantum state tomography, recently. Then so that was for the pure state, as someone was pointed out, but then this was generalized this year to mixed states through purifications, which I won't discuss today. But in this talk, finally, what time is it?
It's 10 minutes to 7.
Okay, so this is really bad. Okay, so we parameterize the Born rule, which is the probability of the outcomes that we see. So that's what we're going to use. We parameterize this statistics that we observe in the experiment using generative models. Okay, and then we use some set of measurements, which is not important. It's just a different big bunch of operators that we have to measure, or measurements that we have to apply on the device, and then we produce an answer for the state that looks like this in terms of this tensors that I'm going to define. Okay, so the reason why I introduce this notation is because this is the type of states that we're going to be using, right? Like they look like this. So this is matrix, right? Because so this is basically my density matrix. So I'm not going to explain this in a lot of detail, but basically this is this mathematical description of the set of operations that we're going to apply on this device. So it's basically what people call positive operator value measures. And the most important thing that I want to say is that they're informationally complete. It means that the information that you have here in this distribution, this P of A, which is the probability of the measurements that you see when you go and measure the device is related to the density matrix that we want to estimate. And the idea is that if you take one set of measurements defined this way, this relation can be inverted. Okay, so that's the only important observation that I want to make. And the other observation is that these measurements are experimentally doable. For instance, in these gate-based quantum computers that you can even access online, for instance, these operators that we're going to measure, you can go and log online to IBM Quantum Experience, and you can ask this machine to produce these measurements. Okay, so this is an experimentally relevant procedure.
Sorry, I don't know that much about the context, but are these states dependent to each other or independent?
Which?
All these states that we are trying to predict, are these all dependent to each other? Like if one change?
The ones that, so I guess the idea is we will produce a state that we have in mind, or we'll try, and then we measure. And we repeat trying to produce the same state, and we measure again. So we'll pick one state, and then we try to measure it again and again, and then so that every time you run the experiment, the outcomes that you get, they're independent.
So just wondering, for like solving the RDMs, like the ultimate machines, you're probably using something like brief propagation, or?
We use something similar. We use contrastive divergence or persistent contrastive divergence for this.
And is it like exact for these graphs that you have, or is it not? Like if the graph has a loop, do you actually get like exact?
It is never exact. So it's an approximate training scheme.
So just to understand what M of A is, like the eigenstates of that matrix are what you will observe.
That's right.
Yeah.
Measurement. Right.
Okay.
That's right. Okay, let me go ahead. So this is what these M's look like in this tensor network notation that I was explaining before. So you have some physical indices, which I denote here as the vertical ones, and then you have the outcome labeled by this outcoming indices. Okay, so it's just a notation for the measurements that we'll use. Okay, but it's not very important. I guess the most important thing that we have is we have a theoretical description of the statistics that we see in the experiment PA and the relation with the density matrix and these operators that we're measuring. Yeah.
So, sorry, the outcome index labels the eigenstate that is observed.
Yes.
Yeah. Okay, got it.
Okay, yeah, exactly. And then the crucial observation that we made, or that we think it's important, is that we can learn this distribution P, okay, using generative models. Okay.
Sorry, hold on.
Yeah.
Is there anyone that is very, very confused?
So what is rho there?
That's the density matrix.
Density matrix.
Density matrix. Oh, yeah.
So
what you are trying to measure, actually.
right.
Yeah.
Right.
Okay.
I guess yes.
Put in short words, like you want to characterize the density matrix as using as small as possible a set of parameters.
Yeah, if you want, right. That's true in some sense. Yeah.
Okay.
So I guess, okay, so basically the program is the following. We produce an experiment, measure, produce the state, measure, and you get a big bunch of statistics, a data set, a training data set. And then we train a generative model that produces the same statistics. So that's the generative model part. And then
That was what I want to hear.
okay, good. And then we produce. So we invert this relation. So here we have P in terms of rho. The measurements that I've used are such that I can get rho in terms of P, where P is my generative model. Okay, so that's basically the main point. Then the next is the machine learning, right? Like you can get you can use any of these generative models, like the variational autoencoder, restricted Boltzmann machine, GANs, and
Sorry. So just to be clear, the fact that you can invert that expression is due to the fact that the M's are informationally complete?
That's right.
Okay.
That's exactly right. It means you can, so information completeness has several angles. So one of them is what you just said. The other one is that you can span the entire space of operators using these M's. And they are equivalent statements of the informational completeness. Okay.
Can I ask a follow-up on that?
Sure.
So so rho is the quantum state that you're trying to characterize, and there's only one of it. Like there are not many states. There is one state that you want to characterize, and it has many parameters, and that's what you're trying to solve for.
Right.
So normally you grab that expression, and that's just probably a linear system of linear equations. You invert. That's why you're talking about inversion.
Right.
So what I don't understand is how are you using the generative model? Like, let's say you have a generative model that produces the distribution, but your eventual goal was to get rho.
Yeah.
So how do you do that part? Like, how do you get rho out of it? Oh, you're gonna say it?
Yeah. So
that was a good segue.
Right. So the idea is that you can invert the relation formally. Okay. So this is the expression. So this rho here is just okay. It's a gigantic sum. So those two indices are exponentially bad. They're exponentially in the size of the system. But you'd never do that. You just do it formally, right? So in the end, this is the expression in terms of tensor networks, right? Like you have a generative model that is just a giant tensor, but let me just, next slide, I'll propose how to deal with this part, which is the ugliest. And then the rest is easy, right? Like the rest, you just have to contract these tensors, and you contract n of them, just n of them, and that part is, if you want, efficient. But this part is probabilistic, right? Like this block is your P model, okay?
So why are you just constructing n of them? Why that?
Why n of them? Because I designed the measurements, right? Like I introduced, this is the measurements that I'm going to construct and that I'm going to implement. And so if you do this inversion, it turns out that this is the way they look, okay? So it's by design. So we design them such that once you do the inversion, they look like this, okay? But I guess the interesting thing, let me just jump to the conclusion.
You wanted to cover all this today?
I hope. I guess I don't have the slide, but okay, so let me just tell you the important point. So we did this formal inversion, but actually this sums over here, this indices we do through sampling, right? And the reason why we can sample this thing is because this is a probability distribution, okay? And if you sample that, then you can get the entire thing. That's the idea. Yeah.
I'm just wondering. So for the part on the left, I don't get at all. Like I don't get the lower half of the slide. So what are the T inverses and what is the? I get like the left part, but not any of the others.
Yeah. Okay. So when you do, so this is a linear inversion. So it's basically you invert a linear. Like a linear system. So the usual AX equals B, and then you invert. So that's what I've done in this expression. And here, so what I'm doing is showing diagrams for what each of the pieces in the inversion look like. Okay. And so the first object that we need is this matrix T, A prime, and this looks like this. Okay.
No, I get that part. So what is the green box?
The green box.
It's just like formal inversion.
No, it's actual inversion because so this looks like so this is T, the matrix, and the idea is that it has this tensor, this factorized structure, right? Like so, it's products of tiny matrices, right?
Yeah.
So then, because they have because they're so tiny, then you can invert each of them Okay, and so when you could, and then the other observation is inverse of tensor product is tensor product of inverses. So this is a linear algebra,
Yes.
Wikipedia type of thing. But so if you take each of these like small T matrices, then you can construct the inverse of the entire thing, which is usually exponentially challenging, but because of the choice we made, then this is efficient. Okay.
So one green box is the inversion of the entire like set of T matrices,
No.
or just one T
It's
matrix?
just the inverse of this T matrix.
Oh, okay.
And then you just collect a big bunch of them n if you
And
want.
combine.
And the whole thing is efficient because you have to do it only once. And then you pile n of them.
And what is the last one? Like the one where the greens are like with the yellows? So I don't get that at all.
This thing here.
Yeah, yeah.
So, do you agree with this expression
Yeah.
here?
Yeah, for sure. Like the top half, I have no problem with.
Okay,
Diagram.
so this is a graphical representation of this expression. So this part is P. That is, it gets multiplied by T inverse, which is this green here. And then we have M, which are these yellow ones here. All right, and then there are two sums, right? A and A prime. The first A prime is these lines here. That's why I introduced this notation at the beginning, that if I have lines, it means I'm summing. So the A prime sum is these lines here, and the A sum is these lines here.
So maybe what's confusing me is the yellow circles. Like, why aren't they like the bracelets, the traces basically towards the left, connecting to the green boxes?
Because they look like this, right? Like, so this M.
Oh, those are the M's.
Yes.
Okay.
So this is this M's that I introduced earlier.
Oh.
Yeah. Sorry, it's a mess right now, but yeah. So this is the expression for the density matrix.
So basically, T is a magic tool. You have to filter the expansion information to some kind of degree of freedom.
Can you repeat the question?
Yeah, and please speak up when you ask questions so that the camera can pick you up.
Okay. So T, basically the design of T is a magic tool that you have to filter in the exponential information of the wave function to some finite measurements.
So T is so I design the measurements in this form, right? Like, and then I do this linear inversion that allows me to write the density matrix in terms of the generative model and these matrices. Okay, and then so what we do is we train this part only; the rest is fixed. Okay. I guess one observation is that you can think about these ansatz in different ways. So one is, okay, so it's this inversion of the Born rule and so on, but you can also think about it as a factorization of the quantum state in terms of a probability distribution P, which is my generative model, and a set of tensors, okay? And the interesting thing is all the entanglement comes from the structure of P, because the rest is factorized, all right? And as I said before, okay, PA is approximated by neural nets or probabilistic models. Let me give you the experiments. So we'll use G and Z state. They're prototypical states in quantum information. They're basically very simple. They're states where like you have all spins up plus all spin down, okay? And then we add noise, which is basically a model for the coherence, okay? Where a qubit with probability 1 minus p is just intact, so it has the same state, and with probability p, an error occurs. And the error is basically applying Pauli matrices, so matrices that are local on each qubit. So that's my state. So let's reconstruct those synthetically.
Could you talk more about how you're finding the error?
Which error?
So you're saying you're finding this error. Like, how are you finding it?
So it's basically given with probability p, the error that you...
They define.
It's defined. Yeah.
So I have a question. Can you go to the previous slide?
Oh.
Not this one, like the one with the picture. Yeah. Okay. So is this like so the top box is basically what's representing those beads on the left, the loopy ones on the left. So you're replacing that with the generative model, and the yellow circles at the bottom are actually like the measurements that you're making.
Yeah.
So everything's so what is the point of having an easy to factorize matrix in the first place if you're like completely replacing it with an opaque model?
So the point is, so we have a generative model that captures the statistics that you see in the experiment.
Okay.
And then we want to reconstruct the density matrix, not just this distribution.
So the reason you go for that system that is easy to factorize is because you want to be able to check if your model is learning, so you have to have a reference kind of implementation.
You need a state, a quantum state that that represents what you're measuring, right? And so you need not just the probability, you need to attach to it a big bunch of other quantum things, right?
Can you go to the one after this one that you're, yeah, so I didn't get this part. So you find a factorized state and all the information about like correlation and time is
in this part. It's because the rest is, it has a factorized form. So if you remove the generative model, all you get is something that is completely disentangled.
Yeah, okay.
That's the idea. So let me give you a result. So this is just learning 2 qubits, so it's very easy. So for this you don't need a generative model, but we just checked. And what we see here is the KL divergence between the statistics in the experiment, if you want. We didn't have any real experiment, it's just numerically imagining that we performed this experiment. And the KL divergence between the model that we have, that we defined, that we're training, and the actual distribution P, out of which our samples come from, okay? And then it goes to 0 as we train, okay? And this is for an RBM with only 2 visible variables, A1 and A2, and then the hidden variables are H. And so, okay, we see, that it goes to 0, and then the fidelities go to 1. So fidelities are measured distance between matrices, right? It's very similar to, if you want the KL divergence, is a divergence or a distance, quote unquote, between distributions. But so you can define something analogous using quantum states. So we use, for instance, the classical fidelity for distributions, or you can use density matrices for quantum states. And as you see, as I train this RBM, then I get high fidelity of 1. Okay, so that's the idea, that we're able to reconstruct this density matrices pretty accurately.
What are different curves?
The error.
Yes, so different values of the error that I use. So in here I introduce a model for decoherence, and so I have the pure state, which is when you don't have any decoherence, and then I checked for different values of noise in the state. So I guess what I'm trying to demonstrate here is that I am able to reconstruct either pure states of or mixed states once I introduce noise. Okay, so those are the different values of P.
How close to 0 or 1 does it really get?
Good question. I don't remember, but
do you feel good about it?
I do. It goes above 0.9999. Okay, at especially at large noise. That large noise is easier to learn because you basically at some point you just have a completely random distribution, and those are easy to learn. It's just a
and generate.
And generate. Yeah, you can basically draw a random coin. You get it, right? Like at low noise, it's harder. But if you pick the best, so you see some fluctuations here, but if you pick the best, then you get to this number that I mentioned. Okay, then, okay, this is for 2. If you want to go to 80 qubits, for instance, then you have to be more sophisticated. So RBM doesn't cut it. And for that, I use a recurrent neural net language model, so a probabilistic autoregressive model. And then you get, for instance, 80 qubits with some noise, like p equals 0.01, and then you get to the fidelity, which is almost 1, so 0.9988. So fairly good, okay? And then so what I use is just use gated recurrent units, and then I stack 3 of them, and it's really powerful.
Sorry, one question about the RBM. How do you get that bipartite graph? Because like, is that just, so one part, like the H's are the noise that you inject or whatever? Or?
No, so this is basically a probabilistic model that people in machine learning came up with in the 80s. And what you do is you're trying to describe a probability distribution with 2 variables. And what you do is you introduce correlations by defining
the hidden states.
The hidden states. But the hidden states have nothing to do with the physics of the problem. So they're just there to induce correlations that you see in the experiment.
So let me kind of rephrase the question. So how do you, in terms of the dimensionality of the matrices and of the measurement matrices and of the measurement basis and the density matrix that you're trying to estimate, how many of those hidden layers do you have, or how do you define the topology of that bipartite graph?
The topology is given by the model, so it's just basically you have H there, and they're connected only to the visible ones. But those can be as many as you want. So in here I have 4, but they can be 10 or more.
So it's always like a complete bipartite graph.
It is. It has always this structure. Yeah. Okay. This for the rest of the neural nets, and here is. Should I stop now or?
Okay.
Okay. So here I have a sample complexity study of this learning problem. Okay. Sample complexity means how many samples or how big your training should be, or your training set should be, for you to get a fidelity of 0.99. Okay, so here I'm giving you exactly 2 things. So one is the fidelity as function of the number of samples, and then in here is the fidelity, so the number of samples that you need to reach a 0.99 fidelity. And as you see, or as this thing suggests, is as a function of the number of qubits, you only need a linear number of measurements, which is great, right? Because the state is exponentially big, and we're saying that you don't need to measure exponential number of times, you just measure a number that is linear in the number of qubits, which is a little bit counterintuitive because in principle the state space is so big, but the idea is that the states have a lot of structure, okay? So you may be able to learn them with only a polynomial number of parameters, and there are theoretical arguments for why this is so, and there are theorems by Scott Aronson, basically a computer scientist, that if you want support this idea, that this favorable scaling.
So just wondering, this kind of reminds me of like metric embeddings using like random projections, and there you actually have linear scaling with the inherent dimensionality of your data, but it's you have some overhead that is proportional basically to the logarithm of the ambient space. So like if your size is like, if the size of the state space increases, you actually have a logarithmic term. Did you like try to see what the dependence of that slope is on the number of states in the bigger, like
No. I think I don't understand most of what you said.
To be honest. I know, like yeah. So basically the theory is if you have a high dimensional data set that is inherently lying on some low dimensional manifold, and you take like a bunch of random projections that are slightly larger than the inherent dimensionality of that manifold that sits embedded in the bigger space, you can almost like completely localize yourself within the original manifold, but you have an overhead, you have a loss, oh, not a loss per se, but you have an increase in addition to the dimension of that thing that is logarithmically proportionate to, or proportional to the ambient space dimension. So it does vary, but very slowly. So you know, the slope or whatever of the sample complexity, I don't know if it's the slope or intercept, but it's like it's very similar to this case, but I mean, like, I was just wondering if you looked at that, like, if you increase the size of the state space, how does that kind of work with?
I mean, we're here in, like, intrinsically increasing exponentially the size of the state space, right? Like, I'm growing n
Linearly,
from
so yeah.
linearly up to 80 qubits, and 2 to the 80 is just like a
So it's almost like the same logarithmic kind of growth.
well, it's linear, right? Like, it's not logarithmic, it's linear. So it may be, okay, so one thing I cannot rule out with this data is that it's linear times, like, for instance, I cannot rule out with this error bars that it is n log n, for instance. That I cannot, because the error bars are too big, and so I won't know, but it's approximately linear, let's say.
Is there any reason why you got sort of the wonky pattern on the top one for the zero probability of error one, where the reference point is low?
This here,
Yeah, but then it doesn't. All the other trends like look very cleanly linear, and then that one's got that wonky low point, right?
Yeah.
Is that just sort of like error?
I don't know yet why, but so.
Is it meaningful or not really?
So I think so. It is related to low noise, and where in low noise region it's always harder to train. So I couldn't disentangle the origin for the noise. Yeah. But
it is still well within like a linear fit.
Yeah.
Within error bars.
And the error, no, if you want the correlation coefficient, still pretty large, like 0.96 at least.
It's just if you didn't have the 80 one, you would almost think that there was like a
Constant. Yeah.
Yeah, or like it was like leveling out or something. Like there's something else happening, and then you have the last one which goes out.
Right.
So that's why I was wondering.
Yeah, no, as we say in the draft, it's approximately linear. We can't be too confident about what we see. Finally, let me show you the same reconstructions for ground states of local Hamiltonians. Okay, so it's systems that are, this is what you see in real life, right? Like, because life is governed by a local Hamiltonian. So these are two paradigmatic systems. So one is the transaphilizing model with 50 qubits. And this is just comparing correlation functions between the synthetic states, so because we use synthetic data, we don't use experiments, not yet at least. And then we see that the reconstructions match pretty well the correlations that we see. For instance, this is a local expectation value of ground state of this Hamiltonian. And this is also a two-body correlation function, and they match pretty well. And this is the most challenging state that we tried is a ground state of a frustrated Hamiltonian in 2D.
It's called frustrated Hamiltonian.
Yes. Frustration basically means that there are energetic constraints in this energy function that cannot be satisfied simultaneously, like life. Right?
Yeah.
So yeah. So if you take, for instance, 3 spins which are antiferromagnetically coupled on a triangle, then you want that 2 of them are point the opposite, right? But then you have a third one that also wants the same. So you don't know if you anti-align it with respect to this one or with respect to that one. So it's kind of like, I don't know, and so that's frustration. That's how, this is the simplest example, and so this leads to, if you want, to a lot of interesting states, because you do this but multiply by n, right? And so you don't really have a clear picture of what the system is going to do because of these constraints, right? And so these states tend to be challenging to reconstruct or to study because of that. But what we're saying here is that even in those cases, you're able to perform decent reconstructions using, again, this is again the recurrent neural net model, which is funny because what I did was, okay, so these are typically one-dimensional, like for sequences and so on, for language and so on. But what I did was, okay, I don't know what else to do, or maybe I do, but I'm going to try anyway. So, and what I did is I lay down the RNN model in a 2-dimensional like snake, where like RNNs are always kind of one-dimensional unless you do pixel CNN or more sophisticated stuff. But what I did was just simply took the RNN and then basically did a snake.
There are also like graph neural nets for 2D graphs,
Right.
that they use for, you know, code analysis and also molecules. You're going to talk about next week.
Okay.
So like the message passing sort of
Right.
ideas.
Yeah, it could be that I can do better. Yeah. So
but this is pretty decent already.
I thought so. Yeah. So for the discussion, finally.
Hold on, which raises the question. So you just did like a snake, you say, right? Like a one-dimensional scan over this.
That's right.
So does it mean that it doesn't really need to be it doesn't capture the 2D nature of this network?
It captures the 2D, right? Like, but it does so in a funny way, right? Like, for instance, if you want to capture correlation between 1 and 2, that's natural, right? Like, because they're next to each other, and with 3, even the correlations are probably decaying, and with 4, that's okay. But then it brings 5, which is in the recurrent neural net far, like it's 5 steps away, but it has almost the same correlations as it has with 2.
So, but you're doing the recurrence on this dimension. How does it capture correlation on this?
That's what I don't know, right? Like, I brought it for discussion, right? And yeah.
Why didn't you do the snake 4 to 8? Or rather 4 to 5.
4 to
8. So go right. Yes.
You can do anything. It's the same. It works equally well.
Wait, any choice that you make will work?
Yes. Yes.
Have you tried a space filling pattern?
Curve,
Curve rather than
like a Hilbert curve?
Oh yeah.
No.
Yeah.
I haven't tried. So which are those? I don't know what they are.
Like you take the Z motif, but like make it as small as you can, and then fill the space in the same shape, kind of.
Like this?
Yeah. So many
Well, so
small
you
Zs.
get pretty good locality, except for on occasional edges.
Okay, so this is a one to know. Okay, yeah. Simulator.
There was a question. There was a question right over there.
Yeah.
Me?
Sorry.
Well, in the first row.
Oh. Yeah. So I was just going to ask because I know the paper mentioning that graph neural networks are quantum prediction. So why do you take such a linear path? Why not just, for example, in other papers where they have using graph neural networks, each like with this message passing, each essentially recurrent unit gets information from all the ones around it. So why have such a directional approach? Why not just have information coming from a few sides at the same time?
Yeah, so the reason is you need to keep the so this is an autoregressive model, and so basically what you do is you split the probability of all of them basically in terms of probability of 1 times probability of 2 given 1 times probability of 3 given 1 and 2 and so on, and you have to respect this. And this is why I have this 1D pattern, right? But there are pixel CNNs, and they do convolutions and so on, and they respect the autoregressive structure of the model, but I haven't checked that. So I guess that would be a natural thing to do and so on, or maybe graph convolutions, but I don't know.
That'll be very interesting to see what the...
And there was one more question, sorry.
Really low level question, but what are the axes for C and D and the color? What are those plots showing?
So their correlation between this first spin and the different ones are, and there's R is parameterized by N1, which is how many distances along this direction you go, and N2, how many along this direction. So basically, it's a two-body correlation in this two-dimensional space. So for discussion, I guess this is things that I don't know, but that I want to ask you, right? Like, so how to develop intuition for which generative model to use given a physical state, right? I guess I don't know that. So is it?
So do you expect that different states will need different models?
I expect that, yeah. The same way, for instance, that in machine learning you expect, for instance, one model to work well for language, but not for vision
But
and so on.
doesn't that impose like a problem if you're going to test, like suppose that you have a machine and you're producing many different states and you want to test for a range of them, so you'll have to have enough models for each of the states?
I think so, yeah.
Okay.
That's a limitation.
What's an example of like some different physical situations, just so I understand what you're.
Yeah, for instance, in here I wrote spatial dimensionality, and so in here I have a one-dimensional system, and so in one-dimensional systems I was expecting recurrent neural nets would work because these things look like a sequential, or there's a one direction like time and so on, but then I tried in 2D and it worked equally well, where I don't have this more natural way of organizing the spins, and it works, but I don't know why.
What about using like convolution, one-dimensional convolution?
Right, like that's the point, right? Like I don't know.
I see.
Right. So we need better understanding of the models and so on.
I just want to say quickly that like 1D convolution doesn't inherently have a sequential nature that, but his you had a 2D model too, so.
And then the other question is why RNN is still so effective in 2 dimensions. So when I saw that, like I tried a big bunch of other systems that are 2-dimensional, and everything, like it always works. So it learns to do these jumps, right? Like it always learns this even crazy correlations, right? Like so you go here and you jump from 4 to 5, and this thing is able to capture the correlation, or it knows that 1 is as close to 2 as 1 is to 5. Which is funny, but yeah.
So you're doing iterations, right? Like in this RNN model, like you're going from this one to another one, and each time passing the message, or is it like all simultaneously?
It's all simultaneously, depending on how you define that. But so yeah, so basically you just feed 1, 2, 3, 4, 5, 6, 7, 8, and so on sequentially until you get the prediction for the entire thing.
I think so. To that question, this is generally designed for like one system, like one size of state. So there's no transfer from like one size to the other.
Not in this case.
So probably the RNN just learns the the edge effects of like every 4 steps there's some strong correlation because actually they are kind of adjacent in another maybe.
Yeah, something like that.
Yeah.
But for instance, it's not just jumps every 4, right? Like because this one is correlated with 5. Strong, and okay, that's the 4, but then at 9 it has to know that it has the same jump as like the same correlation as 3, for instance.
Yeah.
So
it's learning, but like it's learning one periodic function in terms of like the structure. So
is it periodic? I don't know.
it's almost like periodic, and
Almost
there's the
periodic.
edge effects, but
So it learns basically this structure.
That's what I was thinking too. Because you're going in such a, well, why does it work well? Because you're not actually going like 2-dimensional. That's the thing. Like
But that's a restriction of the model,
right? That's a restriction of the model. So you're going 4 to 5, and then because you have that, you're saying you're finding that correlation from, let's say, 5 to 2. And then you're going from 5 to 6, and that's why, because it has all those correlations, and the 2 has to 3, you still, because it's like part of the previous one, that's why maybe it's sustained into the next node, right?
Yeah, maybe. Because we'll have to figure it out, but yeah. And finally, some regularization issues, but I didn't have time to discuss those.
Cool.
All right. Thank you.
So I think we have time for more questions if people would like to ask.
So are quantum states easy?
Yeah. These states are easy, it seems.
For
So
who or
like-
what?
Sorry.
For who or what is the key question there.
So like what is, like do you know what is the category of states that are, like for example with MPS, you kind of know what kind of states are easy to describe, right? So do you have enough understanding?
No. Not yet.
So basically, for short-range correlation, dominant can be much easier.
Sorry, can you?
For short-range correlation, quantum states, it will be easier.
Yeah, that's fair. That's fair to say.
I might be completely completely wrong, but I'm thinking like the RNN, if you're doing like a straight like line, like state after, so that kind of factorization, it's you can kind of treat it like a bit of a decoder. So did you try to just to see like if the RNN, if the state space is large enough of the Markov chain decoder is large enough to represent your kind of system states, then it's kind of obvious because it's a very good fit for the problem. Did you ever like try to make the RNNs like artificially super small, like super small cells? Like what was the dimensionality of the cells?
100.
100.
So I haven't explored a lot of these questions. Yeah, that's a good question.
What other models are you looking to use or to test? Right?
So I want to test like pixel CNN, for instance, that I want to check in 2D and see if it works better and so on. I want to test the GANs, but the problem with GANs is you get their power, but you also don't have an explicit density, which I usually like, because then it allows you to compute a lot of diagnostics for the reconstruction and so on, which maybe people don't care, but for this type of certification, it's important that you know what the probability P of X given some vector is, and with GANs it's just much harder and so on. And,
Can you go back to the previous slide? No, sorry, the next one there. See? The one that had the triangle, the frustrated.
Oh. This one.
So it can't, like the horizontal correlations, interactions can't be captured by the factorizable part of your description, right? Because what I'm thinking is that for your RNN, essentially, like you can literally grab your red lines and stretch them, and that would be just a line, like that's how
it is a line, yeah,
right?
Yeah.
So I'm trying to figure out like what is capturing the horizontal ones still, and the factorizable part can't be capturing those. Is that right? Or can it be captured there?
So I don't have a very good answer.
Maybe like the selective forgetting, if you use GRUs, they're not like straight up, you know, they can actually selectively like fast track certain state through like a few steps ahead. So like, you know, they're yeah.
Yeah, but I mean, essentially, which is a simpler just structure to get this, just less, one less matrix multiplication, right? As compared to our LSTMs, if you're saying.
But the thing is that
so it's basically all I'm saying is that there is less, like that argument wouldn't help.
No, like the Markov structure. So basically,
like
I don't know. Let me think.
If you look at the red lines, that's not a frustrated network. That's just a line, right? And like using GRU or RNN or LSTM wouldn't make a difference, I don't think, because it is not capturing any of the horizontal interactions. Like that has no idea that 4 and 8 are connected. Like red lines have no idea 4 and 8 are connected.
How strong are those? I think that's important too. How strong are those connections? Like the horizontal ones? Because if they're
they have the same strengths according to Hamilton.
Yeah.
The thing is,
Just J.
Oh yeah, please go ahead.
So I noticed you run through it sequentially with this RNN, right? But aren't there reverse relationships as well? Like, or does it not, like, this second state is based on the first one, but isn't there a relationship in the other direction as well?
And
it's one direction.
It's undirectional.
Undirection. So, but the RNN is running through this sequentially 1, 2, 3, 4, 5, whatever. But isn't there relationships 5, 4, 3, 2, 1 as well?
Yeah,
and so you can never capture in one the stuff that you see later, because.
Right. So, but this is a choice, right? That you basically arbitrarily pick the numbering of the spins, right?
Yeah.
So you can start from here or from here, anywhere.
So you can start at the end and go backwards.
Yes,
and
you can do the learning this way. Yeah. And you would learn the right correlation. Yeah.
So for the RNN side of the quick clarification, so Alex, were you asking, were you comparing it with the vanilla RNNs or LSTMs?
With like vanilla RNNs.
Oh, okay, so
I'm
that's
just
why
thinking,
I-
yeah.
okay.
And the red line probably just corresponds to our to the machine learning model. Like the lattice itself is obviously there, but we are like modeling the states through that, so we don't have to capture like the Markov structure,
Yeah,
like the neighborhood structure.
Yeah, I
of
get
the
you. So
original
my
stuff,
comment
yeah.
was if you were comparing with the LSTMs, they should.
No, I was not
that makes
comparing with
sense.
LSTMs.
So then a follow-up question on that, at this time from the speaker. How I don't understand the problem space, the physics of it as well as some of my colleagues do here, but how much linear dependency is there in the data to predict? How far back in your, if you're using a recurrent model, how far back do you need? What's the long distance dependency in your data?
So that's a good question, and as you can see probably from this correlation, it decays relatively fast. So that's probably helping, right?
Yeah, so that would make it easy for the RNN to predict, right?
Right.
And I would guess if you just use a hidden Markov model, like maybe a simpler sequential.
Probably yes, yeah. It's just that the RBM didn't work.
Yeah.
In this.
Situation. Okay, fair.
So I went to this autoregressive and it worked, so I was happy. But of course, there's a lot more to be explored if you want.
So, let's say from node 5 to 1 and 2, is it taking, so it's getting information from both of them. My question is it taking information at equal weighting? Or is it different?
There's a constant weight, the J is constant.
Yeah. Okay,
J
so
is
constant.
constant.
Okay.
Yeah.
And so when you do the RNN, do you find that there's still a constant weighting of those nodes to that node, to the receiver?
So meaning that if I measure the correlation between 1 and 5 and 1 and 2, they are the same.
They are the same even with this RNN?
Yeah. I mean, this is the RNN correlation, right? Like, so with the correlation between 1 and 5 is so sigma 1 and R of 1. So it's this one here.
Got it.
And this is the one with 2.
Yeah.
So as you can see, they're the same. And this is predicted by the RNN with that snake. Yeah.
Okay, yeah, that's crazy.
I think so.
Yeah, that's crazy.
Can that be the explanation, that you're looking at a particular state that doesn't care much about the horizontal interactions? Like if you look at a different state, that might be important.
But the interactions are the same. Either you're like if you go this way or you go this way. So it's more like the RNN figures out that after you go to a certain length floor, you have to build correlations.
So I'm confused about something. So the correlation between 1 and 2 should be the same as 1 and 5.
That's right. Yeah.
But in the table 1 and 2.
So 1 and 1 is this one here. 1 and 2 is this one.
And 1, 5 is?
Is this one. And they should be the same, and they are, right?
So then I don't understand the indexes on the left.
Yes. It's how you move
moves
along this direction or that direction.
So whatever direction you go, it still always has the same weightings.
Oh yeah, I mean
That's
you
so
see
cool.
more or less that this
That's
thing
so
is symmetric. Yeah. So yeah.
I think that this point may have been addressed, but just want to re-raise it. But I think Alex was also mentioning it earlier. So there seemed to be a pattern, like irregularity in your
Yeah.
So if that's the case, it's also not long distance.
It's not super long distance, but the predictions match pretty well, even at long distance, right? Like so, there's numbers when you compare them like number by number, which I don't have a plot that hides everything, but if you go and compare number by number, they're okay even at long distance, right? Like so, this has this decays I think algebraically, if I remember correctly, as function of distance, and this is predicted reasonably well. So it's not that the correlation is absent, and it has a particular form and it is relatively well captured. So I agree that it's weak as you go away, but it predicts these jumps, right? Like for instance, when you go to 2 and to 5,
so
it reappears, right? Like because the RNN looks like this, right? As you go through the lattice. So you see a lot of correlation, it decays, and then suddenly it jumps when it comes here, and then it decays again. It jumps, but it's not to 1. It decays. It knows that it has to decay somehow, some more, as you go. So I don't know.
So clearly, like you get these right correlations. Now, my question is actually different than last one's. What can this now be applied to? Like this, but we don't know how exactly it works yet. But let's say it works, because it seems to work, but we just don't know how. But since it works, what can the fact that it works be applied to?
Yeah. So suppose you buy a quantum computer, okay, and then your vendor says, I can produce ground states of this Hamiltonian, okay? Then you can check if this, so what you do is you go ahead, you say, okay, you prepare that state, you promise that, then you go ahead, you try, you measure the device, you take that data set, you reconstruct what you got, and then you produce this. Is it the same as what you expect? And if you do, then fine, and you don't feel that you wasted $10 million.
It's like a benchmarking test?
It is a certification.
It's
like QA. Like an ECC ramp for like quantum computers or something.
This is the new version of the requirements testing that Windows has.
Sort of.
Yeah.
Are 0, 2 and 2, 0 supposed to be the same? Like in the synthetic state.
0, 2? Oh, 0, 2?
Yeah, and 2, 0.
And
I'm trying to
like
figure out,
there,
based on a like very subjective assessment of color,
yeah,
whether it actually is doing better when it's going along the lines that of the sequence that you fed into the RNA.
Probably
because
yes. Yeah.
It kind of, again, based on this subjective assessment of color, it kind of looks like it matches better when you're moving across rows than when you're going down. So like if you look at 0 in the column, like row 0, and then 2 to 3, and like that line, versus if you go the other way, the pattern of like dark, light, dark along the top matches better than the pattern of like dark, light, dark on the side.
It's probably
confused so much. I was like, what?
If you're on row 0 and you're moving across that top row, it's like very dark, white, dark, light, dark-ish, right? If you're on that top left corner moving down, it's like very dark, light, dark, slightly less dark, which isn't quite the same as what's happening in the synthetic one. So I was trying to.
But that makes sense, right? Like because this part.
Because you're moving actually along that sequence.
So this is the easiest to predict.
Right.
Because this is actually sequential, but then you have jumps, and then you start to predict this thing, which should be the same as this, but through.
So that made me start wondering about that, like in the synthetic one, which is what it should be, whether it is symmetric across.
Probably not exactly symmetric.
But you're saying that the connections are the same. Like you're saying that 2 to 5 and 1 to 5 is the same. So surely even if you go through this RNN, these horizontal connections should still influence it in the same way as if.
They're not exactly the same because of the edge effects, right? Because like if you have things in the corners, they're connected to different numbers of.
No, but he's saying he's saying that they have the same like.
I didn't say exactly the same.
Okay, sorry. Sorry, that's
similar, almost the same.
Sorry, forgetting stuff.
Yeah,
it's probably forgetting. So I have to have.
So I'm just wondering, does it take a lot of work to actually run and sort of forward pass on this system? That's what you're showing us here, right? This is post-training, this is the forward pass, and so. Like, is it a major operation to actually do an inference like this?
Okay, so I did it on the 8x8.
Yeah.
It's not too bad.
Okay.
To produce, because I need to produce data.
Yeah.
In principle, that is synthetic, but if you go to 10x10 or 12x12, there's no way of doing it.
Even with this technique. Even with this technique, you can't
No,
use the.
so okay, so the
RBM.
reconstruction on a large system is very easy. So doing this reconstruction takes 5 minutes.
Okay.
Okay.
Okay, that's
But-
basically what I want to ask. Because what I was wondering is, can't you just train a few nets that do different sort of sequential patterns, and then just sort of average their results, like sort of combine their results? So you could have one net that's going left and right, and one net that's going up and down, and one net that's going on the diagonals. And if they're easy to run, then you can get the different effects and combine them.
Maybe, yeah. But I don't know how to do it in practice, but.
So I have a question, like, regarding applying this to verifying your quantum computers. So with, and this is only because it's very similar. Like the RBMs are very similar to error correction coding on storage. So like Amazon S3, they actually do have they do code their data at rest, and so they can detect errors like hardware failures and stuff like that. And a lot of effort is spent basically verifying, finding the tracking sets and all the other things about your code to make sure that it doesn't have some pernicious failure modes. Would there ever be a principled way of understanding the failures of this? What kind of states might actually cause this? Once is there any way of maybe 200 years in the future, actually specifying a protocol that's principled and can actually within that finite regime of networks that we have, or neural nets or inference networks, find ones that are specifically free of certain defects? In a sense.
I don't know. So I'm bad at predicting the future.
Aren't we all?
But I don't know. That I don't know. I mean, this is just baby steps, right? Benchmarking. So
Because
I don't know.
the reason I'm asking, we are kind of fairly limited to states that we can kind of symbolically state and solve, and then cross-validate with something like this. So we never know the entire space that we have not explored. How does it operate? So there's no kind of theoretical bound or what have you on the on how it's actually going to perform.
So there are diagnostics for states, right, that are hard to produce and so on, that we cannot produce classically. For those, we have some diagnostics, maybe not a state reconstruction, but ultimately there's no hope, right? If quantum computers are going to win, we won't be able to certify them rigorously.
Well,
is that right?
It's a question.
I think we'll just take the one last question.
So what I was trying to get to is basically, have you tried asking models that don't have a constant J, but have variable interaction strength between the qubits? Because then you would get rid of that problem that basically right now you might assume that the RNN is just learning the symmetrics of the topology of the graph instead of actually learning the correlations.
So I don't fully agree with what you just stated, that it's just learning the topology, because it's learning pretty fine-grained details of the correlation functions that depend on the specifics of the Hamiltonian. Okay, so it's not just the graph structure. Because if it was the graph structure, then why do we have all these details, right? This accurate values of the correlation function that depend on the graph, but also on the nature of this variable. So here I have spin 1/2 variables, but if you change them to say spin 1, then the nature of the correlations would be completely different, right? And what I'm saying is I can't predict those subtleties about the correlation functions and so on. Of course, there's a big component, which is the graph, and that it seems to be getting it right, but there's, I think, something beyond that is specific to the state. I don't know if you agree, but.
Okay, so thank you so much.
Thank you.